Okay. You guys have any question? I always have my office hours, so you can always come, or you can write an email, or you can Zoom. So I will take time this week to grade your homework. Yeah, having a lot of exams to do as well. So I will work on that this weekend or this week. Okay, let's continue from where we left. So we were doing the null space and column space. So we were looking at the column space. So we say the column space on the null space of an M by N matrix, which you can write as that, is a solution of the homogeneous linear. So what you get in X and solutions of the null spaces. So now the solution of null space. So which defined by the solution. Okay, so we were looking at this theorem here. If A is an M by N matrix, then the null space of A is a subspace of Rn. So if we remember, we say the column space, so away from this, the column space of A, the column space of A is subspace of Rm, right? It's a subspace of Rm. You still remember that. So the column space, if you still remember, is a span of the vectors A1, A2, all the way to AN. As long as when you reduce it, then the augmented matrix is consistent. So the vectors that are giving you consistency are the ones which are the column space. Okay, let's try prove this theorem. If A is an M by N matrix, then the null space of the subs is a subspace of Rn. So we can try prove this a little bit. So if what we want to do is we want to prove whether A zero vector is equals to zero vector. So the null space, we say, is a solution of homogeneous linear equation. Then it means that zero vector is an element of null space of A. It's the element of null space of A. Now, if we let U1 and U2 to be the elements of the null space of A, and C1 and C2 to be the elements of real number, then AU1 is equals to zero vector, and also AU2 is equals to zero vector. Is equals to zero vector. Then A and then C1 U1 plus C2 U2 is actually equals to the same as C1 AU1 plus C2 AU2. And we said this AU1 is 0, so C that plus C2 zero vector, which is the same as zero vector. Which is the same as zero vector. So therefore, C1 U1 plus C2 U2 is actually the element of null space of A. Null space. So therefore, so the null space of A is a subspace of Rn. Rn. So Rn is basically the number of what? If it is a matrix, then it is the number of columns. So in this case, what we get here is that if the solution is this, then here it is in R2 because we have two solutions here, which is U1 and U2. So basically, this is the same as the span of U1 and U2. And this span of U1, U2 is actually the element of null space of A. Element of null space of A. We'll see an example on this and we'll see what we mean. Okay, now let's look at another example. Example number, I think number 5. If we let A be an 5 by let's say 4, a 4 by 5 matrix, 4 by 5 matrix. Give integers P and Q such that null space of A is a subspace of Rp, and column space of A is a subspace of Rq. So what will be P and what will be Q? For the null space of A, we say the null space of A is the same as what? Is it Rn, right? Is it Rn? And if this one is M by N, then that means the M is our. Then for column space of A, then it is M. So therefore, the solution here is for the null space of A, then this is actually the subspace of Rp, where P is the number of what? The number of columns. The number of columns. And the column space of A is basically the subspace of Rq, where Q is the number of rows, the number of rows. So the number of columns here are, are 5, right? And then the number of rows are 4. So basically, our P here, so P is equals to 5 and Q is equals to 4. P is 5 and 4. Anyway. Okay. Let's look at another example, example number 6. if we let A to be equals to -3, -2, 0, 0, 2, -6, 6, 3, and 3, and U to be equals to 1, 14, and -9. Okay, number A, let's determine whether U is in null space of A. Let's determine whether U is in the null space of A. So how can we determine that U is in the null space of A? So what we need to do here is the solution. So what we need to do is we need to actually determine whether AU is equals to 0 vector. So what we need to do is determine whether AU is equal to 0 vector. So you need to multiply -3, -2, 0, 0, 2, -6, 6, 3, 3 by U, which is 1, 14, and -9. 1, 14. So if you get a 0, you get a 0, 0, 0, it's a 0 vector, then U is in the null space of A. U is in the null space of A. I notice some of you do not remember how to multiply the matrices. So I said you can use 2 ways. So you can actually take this, multiply by 1, take this one, multiply by 14, take this, multiply by -9. And then you do what? You add, right? Then you add. Or you can use the row and the column. So you do this and this, do this and this one, and then do this one. You can look at the one which is easy. So the easiest is actually taking this and this plus this and this plus this one and this one. You get a fast entry. The next one is this and this, this and this. So if this matrix is actually 3 by 3, and then you multiply this matrix by 1 by 1. 1 by 1. So what would be the solution here? What would be the solution? 3 by 1. Yes, so this are 3 by 1. So the solution is this and this. 3 by 1. So you should get 3 by 1. So this is equals to what I got is -31, 82, and 21. Basically, this is not equals to 0, 0, 0. So this is not equals to 0, 0, 0. So therefore, so U is not in null space of A. U is not in null space of A. Number B. Describe the subspace which is null of A of R3. Describe the subspace null of A of R3. So here, what we need to do is we need to get the solution of AX equals to 0. So we need to get the solution of AX equals to the 0. We need to get the solution AX equals to 0 vector. Now we already have the A here. So basically the vector matrix equation here will be now the matrix A. So then our augmented matrix, which is A and 0. So that will be our augmented matrix. Then you now reduce this completely to get a solution. Of X. The solution of X. So that solution of X is actually the null space of A. So -3, -2, 0, and then 0, 2, -6, 6, 3, and 3 there. And then we add our zeros here. So when you reduce this matrix completely, because we have done this one severally, I don't want us to waste time doing it. So when you reduce this matrix completely, then what you get is 1, 0, 2, 0, 0, 1, -3, and 0, then 0, 0, 0, 0. You can go try this on its own. That is what you get once you reduce it completely. So that means you get the pivot position here. So you make this one. So here, now our new linear equation here will now be x1 plus 2x3 equals to 0. And then we have x2 minus 3x3 equals to 0. So basically, we have our basic variables as x1 and x2, and our free variable as x3, as x3, or free variable as x3. Then our solution set here, which will be x, is now equals to x1, x2, x3, which is equals to taking this x, making x1 the subject, you take this x3 to the other side. So what you get is minus 2x3. Taking this x3 to the other side to get x2, you get 3x3. And then our free variable, which is x3. And then x3 there as our free variable. Take this to the other side to get this. So x1 will be x2. Take this one to the other side, which will be our x2 will be x3, and then our free variable which is x3. So this is now equals to factor out x3, which will be minus 2, 3, and 1 there. Minus 3 and 1. For what? For any x3. For any x3. Now, this is our solution set. This is our solution set of the homogeneous linear equation. Therefore, the null space of A is now the solution set. So the null space of A is now equals to x3, -2, 3, and 1 there. x2, x3, -2, 3, which is basically the same as the span of -2, 3, and 1. The span of. So this is solution. solution for solution for null space. Any question after that? So we'll see more examples of this, how to get a null space, call null space. But basically what you need to remember is to get a null space, then you need to get a solution of the homogeneous. You use it completely. Then the way we were just doing last time, then what you get here. So these vectors here are the solution for actually for any x. Okay. Now let's come to the next section, which is the basis for this. 3, the basis of a subspace for Rn. Basis for subspace Rn. So we already had the subspace, which is H. So we have the large space, which is Rn. And then we took a small section, which is H. Now we want to know the basis for that H. So we want to know the basis for that H. So let's look at definition 3.1. If we let H be a non-zero subspace of Rn. So it's a small section of Rn, and which is not zero. Then a basis for H is a subset, which you can say beta. The basis for H, which is subset beta of H, such that number one, the vectors in beta are linearly independent. Number two, beta spans H, i.e., every vector in H is expressible as a linear combination of vectors in beta. So that is actually the definition of basis, which we've already defined the basis in the whole space, which is the same basis. So if we take that small section, which is H, and then we take beta to be the basis of that H, then that beta, for it to be a basis, then it's actually linearly independent. And also, if it is linearly independent, then it spans H. Basically, for it to span H, then it is a linear combination. So it is a linear combination. For example, okay, before we go to that, now we define the empty sets to be a basis for the zero subspace of Rn. We define an empty set, the basis of the zero subspace. So empty set can also be the basis of the zero subset of Rn. Okay, example number 7. So how can we define that basis? So let's look at this example. Show that the standard vectors, which is E1, E2, all the way to En, is a basis for Rn. Is a basis for R. So to show that this is a basis for Rn, then it should satisfy the two properties there. So first of all, one, it should be linearly independent, and the other one, it should span change. Now, looking at these are actually the standard vectors, which are 1, 0, 0, 0, 1, 0, up to the last one, which is 0, 0, 1. Okay. So when you put it in a matrix form, and then it is already reduced. So if we have the pivot positions in each of those vectors, then if we have the pivot position in the column and the rows, then it means we have trivial solutions only, right? So we have trivial solutions. So if we have the trivial solutions, then it means that there is linearly independent. So if it is linearly independent, so basically it will span, it will span H. It will span H. So to prove this, then we note that if we put this one in matrix form, E1, E2, all the way to En, is actually the same as the identity matrix. So if we put that one in matrix form, so it will give us the identity matrix. To give us the identity matrix. Then, number one, for this identity matrix, then basically it is an n by n. So the n by n matrix, In, has pivot or has n, put here, n pivot positions. So it has n pivot positions. So it has n pivot positions and it is an n by n. Then basically that one is what? Then the vectors E1 all the way to En are linearly independent. Number two, every row of matrix In has pivot position. So E1, E2, all the way to En spans Rn. Span Rn. So basically, so E1 to En, the vectors E1 to En are basis for Rn. So basis. Now let's look at another example. Example number 8. Show that the vectors B1, B2, B3 is a basis for R3, where B1 equals to 1, 0, 0, B2 equals to 1, 1, 0, and B3 equals to 1, 1, 1. B3 equals to 1. Show that B3 is a basis for that. So how do you show this? So what we need to do is we need to check whether it is linearly independent and also if it spans R3. It spans R3. Okay. So number one, the proof. So number one, the 3 by 3 matrix, which will give us a matrix B1, B2, B3, has 3 pivot positions. So if you look at that, it is actually having 3 pivot positions. We put this on the matrix form. So we have the pivot position here, and the last one here. So it has 3 pivot positions. So B1, B2, and B3 are linearly independent. Number 2, every row of matrix B1, so don't forget these ones are vectors, B2, B3, has a pivot position. So B1, B2, B3, all these are vectors, spans R3, spans R3. And so B1, B2, B3 spans are actually or is a basis for R3. It's a basis for R3. Any question after that? Okay, example number 9. Display an echelon form of a matrix A. So this example displays an echelon form of a matrix A. Now find a basis for the column space of A and a basis for the null space of A. Null space of A. If we are given the A, which is equals to 3, -1, 7, 3, and 9, -2, 2, -2, 7, and 5, and -5, 9, 3, 3, and 4, and then -2, 6, 6, 3, and 7. If this has been reduced to echelon form, we get 3, -1, 7, 0, and 6. And then 0, 2, 4, 0, and 3, and then 0, 0, 0, 1, and 1. And then this is 0, 0, 0, 0, and 0. And that is the echelon form. Then what is the column space of A? What is the column space of A? So the column space of A are actually the vectors which are giving us the pivot dimensions. So 3 is a pivot dimension. 2 here. So for the column space of A, then the ones which are the vectors which are giving us the pivot positions are now the basis for the column space of A. So this will now be our basis, which is the first vector. This one will be another one, and this will be for the column space of A. For the column space of A. So we can say solution. We can denote the columns of the matrix A by A1, A2, A3, A4, and A5. So we can denote those to be the columns. These are actually vectors. So basically, we can take this as A1, A2, A3, A4, and A5. So if we take those ones like that, now since, so number A, or number 1, since first, second, and third columns of A are pivot columns, the vectors. So if you look at this, so this one is, so this is the pivot position, this is the pivot position, and this one is the pivot position. So the pivot columns are this one, this, and this. Now, since those are pivot columns, then the vectors A1, which is equals to 3, -2, -5, and -2, A2, which is equals to -1, 2, 9, and 6, and A4. A4, which is equals to, actually, this is a 4th. A4, which is equals to 3, 7, 3, and 3. So if these are the ones which are giving us the pivot positions, then basically these vectors A1, A2, and A4 will now be what? Linearly independent. They are now linearly independent. So basically, these A1, A2, A3, A4 are linearly independent. So they are linearly independent because each of that, if we reduce this, then we find the pivot position in each of the columns. So if these are linearly independent, then therefore, if B, which is an element of column space of A, if B, which is an element of column space of A, then AX equals to B is consistent. AX equals to B is consistent. Therefore, our AB, which is now our vector there, or our augmented matrix there, is equals to, we can take this as 3, all these are 0, 0, 0, -1, 2, 0, 0, 7, 4, 0, 0, and then 0, 0, 1, 0, and then 6, 3, 1, and 0, and then if we put this one S or B, which is that. So that is, when we reduce this now, when we together reduce, we put this on augmented matrix form, then we can find that this is our pivot position, this is our pivot position, and this is our pivot position. So that is our those are the pivot positions. So therefore, then it means that A1, A2, and A4, and our B there are equals to or are equivalent to this matrix here, which is 3, -1, 0, and that, 0, 2, 0, and that, and then 0, 0, 1, and that, and then we have 0, 0, and 0 there. So it will be equivalent to. So when we reduce this, we get this. Yeah. So we use that matrix over there. Now, since we have the pivot positions in this one, in this, then we take now this one, A1, which is this one, A2, which is this, A4, which is this one, and then our B, which is this. So looking at this, then this is our pivot position, this is our pivot position, this is our pivot position. So we find that we get all the pivot positions in each one of them. So this matrix now here is giving us the pivot positions in each of them. So if it is a 3 by 3 matrix, we can ignore this. Then we have 3 pivot positions. So if we have 3 pivot positions there, then therefore this matrix here is linearly independent. So it is linearly independent. So if it is linearly independent, then so our vectors here, which are formed from that, which is now 3, -2, -5, -2. -1, 2, 9, and 6, which are for A2, and A4, which is 3, 7, 3, and 3. Is a basis for column space of A. Is a basis for column space. So what you need to do is reduce that matrix. Reducing the ones, the columns which you're giving the pivot positions, you separate them. So you separate them. The ones which have the pivot positions. So once you separate them, then those vectors which are from that reduced matrix form are now the basis for. Because we know that for it to be a basis, then they should be what? Linearly independent. They should be linearly independent. Any question after that? Okay. Now, for it to be a null space, which is number 2, to get the null space, now the null space of A is now the solution of AX equals to 0. The null space of A is the solution. So we are already given the reduced matrix, which is this. So the solution here will now be, so you now take now the 3 -1, 7, 0, and 6, then 0, 2, 4, 0, and 3, 0, 0, 0, 1, and 1, 0, 0, 0, 0, 0. And then you do what? You add 0, 0, because you need to solve this. So you need to solve AX equals to 0. So you bring that to. So when you reduce this completely, so you reduce now this one completely. So when you reduce it, what you get is 1, 0, 3, 0, 5 over 2, and then 0, 0, 1, 2, 0, 3 over 2, then 0, and then 0, 0, 0, 1, 1, and 0, and then 0, 0, 0. So that is what you get when you reduce it. So what you need to do first is make this one to be 1. You multiply by 1 over 3. Or you can start before you do that. So since this is a pivot position, this one is a pivot position. This is already 0. So these are already 0. So you're good there. So you come to this, you make this one 0. So make this one 0. Then after that, then you make this one 1, and also you make this one. So before you even make this one to be 0, then you need to make this one to be 1. So you multiply by 1 over 2. Okay. Multiply by 1 over 2, then you can subtract to get this and this. Then you now multiply by 1 over 3. Then you get this. So therefore, this matrix is giving us our basic variables as x1, x2, and x4, and our free variable as x3 and x5. So now you put that in the solution form. You now bring this one, put this on the linear equations, and then put that in the solution set, and then the vectors that you get from there are the null space, So we'll finish this next Friday. Okay, have a nice day. So,
Hi, I was wondering if our exams are graded.
yeah, I really graded them. Oh, you did not try.